Every time you send a message, watch a video, or load a web page, your data is doing something pretty remarkable. It's not just traveling from point A to point B in one piece, it's getting chopped up, sent down different routes, and then reassembled at the other end. That's packet switching, and it's basically the reason the internet works the way it does. So, what exactly is packet switching and why does it matter? Packet switching is a method of transferring data across a network. Instead of sending information as one continuous stream, the data gets broken down into smaller chunks called packets. Each packet travels independently to its destination, where they all get reassembled into the original message. Think of it this way. You want to send a large photo album to a friend across the country. You could send the entire album in one big box, but that's risky. What if the box gets lost or delayed? Instead, you tear out the photos and mail them in separate envelopes. Some might go through different post offices, some might arrive out of order, but eventually your friend collects all the envelopes and puts the album back together. That's essentially what happens every time you use the internet. Before we get into how it works, we need to understand what came before it. The older method was called circuit switching, and it's still used in traditional telephone networks. Circuit switching works by establishing a dedicated connection between two devices before any communication happens. Once that connection is made, the channel stays reserved for the entire duration of the session. No one else can use it until the call ends. It's like reserving a table at a restaurant. You call ahead, book a table for 5 p.m., and that table is yours, even if you show up late or don't use it the whole time. It's dedicated to you. Circuit switching is great for voice calls because the connection is stable and consistent, but it's not efficient. If you're not talking, that reserved channel is just sitting there unused. And if you're sending data that doesn't need a constant connection, you're wasting resources. That's where packet switching comes in. In packet switching, there's no dedicated connection, no reservation, no setup phase. When you send data, it gets divided into packets right away. Each packet contains a piece of the original data plus some extra information, a header. The header includes things like the source address, destination address, and a sequence number, so the receiving device knows how to put everything back together. Once the packets are created, they're sent out onto the network. And here's the interesting part. They don't all take the same route. Each packet travels independently, hopping from one router or switch to another, choosing the best available path at that moment. Some packets might take a faster route, some might encounter congestion and take a detour. Some might arrive out of order. But that's okay. When the packets reach their destination, the receiving device uses the sequence numbers in the headers to reassemble them in the correct order. It's like putting together a puzzle, even if the pieces arrived in random order. Packet switching operates on something called store and forward. When a packet reaches a router or switch, the device doesn't just pass it along immediately. It stores the packet briefly in a buffer, examines the header, checks its routing table to figure out the best next hop, and then forwards it. This happens at every switch or router along the way. Store and forward is one of the reasons packet switching is so efficient. Because there's no dedicated path, the network can dynamically adjust to traffic and congestion. If one route is overloaded, packets can take another route. Resources are shared among all users, so nothing sits idle. But store and forward also introduces delay. Every time a packet gets stored and processed, there's a tiny bit of waiting time. It's usually not noticeable for most applications, but it does add up, especially if the packet has to hop through many routers. Another key advantage of packet switching is flexibility. Circuit switching is great for voice, but that's about it. Packet switching, on the other hand, can handle all kinds of data: video, emails, web pages, file downloads, streaming. It's the backbone of how the internet works. And because packets can take different routes, the network becomes more resilient. If one router goes down or a link fails, packets can just reroute around the problem. In circuit switching, if the dedicated path fails, the entire connection drops. There's also the concept of pipelining in packet switching. Let's say you want to send 4 packets from device A to device B. You don't wait for the first packet to reach B before sending the second one. Instead, while the first packet is traveling through the network, you send the second packet right behind it, then the third, then the fourth. They move in parallel, which speeds things up significantly. This is different from circuit switching, where you'd wait for the entire channel to be ready before sending anything. When we talk about the total time it takes to send data using packet switching, we have to consider a few things. First, there's transmission time, how long it takes to actually push a packet onto the network. But here's the catch. Every router or switch along the way also has to transmit that packet. So if your packet hops through 4 routers, you're transmitting it 4 times. The total transmission time is multiplied by the number of hops. Then there's propagation time, the time it takes for the signal to physically travel through the cables or air. This depends on distance and the speed of the signal. If your packet hops through multiple routers, the propagation delay adds up for each hop. So the overall time in packet switching is the sum of all those transmission times and propagation times across all the hops. In circuit switching, transmission only happens once because the path is already established. But in packet switching, every hop requires a new transmission. That's the trade-off. Packet switching also requires headers, which add overhead. Every packet carries extra information: source address, destination address, sequence number, error checking bits. This makes packets slightly larger than the raw data alone. Circuit switching doesn't need headers because the path is fixed and the data flows continuously. But that extra overhead is worth it. The flexibility, efficiency, and resilience of packet switching far outweigh the cost of a few extra bytes per packet. There are actually two main types of packet switching: datagram and virtual circuit. Datagram is the most common. In datagram packet switching, each packet is treated independently. They can take different routes, arrive out of order, and the network doesn't keep track of any connection state. This is how the internet works. Virtual circuit packet switching is a bit different. It's kind of a hybrid. Before sending data, a virtual path is established through the network. All packets follow that same path, so they arrive in order. But the path isn't a dedicated physical channel like in circuit switching. It's just a logical route. Virtual circuits are used in some older technologies and certain types of networks, but datagram is dominant on the internet. So, when is packet switching better than circuit switching? Packet switching is ideal for bursty, unpredictable traffic. When you're browsing the web, you're not sending data constantly. You load a page, read it, click a link, load another page. Packet switching handles that efficiently because it only uses the network when needed. Circuit switching, on the other hand, is better for continuous, real-time communication. Voice calls benefit from a stable, consistent connection. That's why traditional phone networks use circuit switching, but even voice is moving to packet switching now. VoIP, or voice over IP, breaks voice data into packets. It's not quite as smooth as circuit switching, but it's good enough, and it's much more flexible. For small messages and data transfers, packet switching is better. For large, continuous streams of data, circuit switching used to be better. But modern networks have gotten so good at packet switching that it's taken over almost everything. One more thing to keep in mind. Packet switching works at different layers of the network model. Datagram packet switching operates at the network layer. That's where IP addresses and routing happen. Virtual circuit packet switching can operate at the data link layer, which is one layer below. Circuit switching operates at the physical layer, where actual electrical or optical signals are sent. Understanding these layers helps explain why packet switching is so powerful. It works at a higher level of abstraction, which gives it more flexibility and intelligence. Routers can make decisions based on network conditions, traffic, and available paths. Circuit switching is more rigid because it's tied to the physical infrastructure. Packet switching is efficient because it shares resources. Multiple users can send packets over the same links without interfering with each other. In circuit switching, once a path is reserved, no one else can use it. That's wasteful. Packet switching also adapts to changing conditions. If a link gets congested, routers can reroute packets. If a router fails, packets can take a different path. Circuit switching doesn't have that flexibility. If the dedicated path fails, the connection drops. But packet switching isn't perfect. The variable delay or latency can be a problem for real-time applications like gaming or video conferencing. Packets might arrive late or out of order, causing lag or jitter. Circuit switching doesn't have that problem because the path is fixed and consistent. Still, modern techniques like quality of service, traffic shaping, and buffering help minimize these issues. Packet switching has improved so much that it's now the standard for almost all data communication. So, what's the big takeaway? Packet switching is the technology that makes the internet possible. It's efficient, flexible, and resilient. By breaking data into packets, sending them independently, and reassembling them at the destination, we can share network resources, adapt to changing conditions, and support all kinds of applications. Without packet switching, you wouldn't be able to stream videos, browse the web, or send messages the way you do. It's one of those foundational technologies that change everything. If you found this explanation helpful, go ahead and like this video. Share it with someone who's curious about how the internet actually works. And if you want more deep dives into networking concepts, subscribe so you don't miss the next one. Thanks for watching.